are many types of radio receivers. They are made in different shapes and sizes. However, since they all serve the same purpose, they have many features in common. Every radio receiver must have an antenna in order to pick the signals out of the air, and a tuner to select the one frequency which we wish to receive. The selected signal is passed into the detector, which separates the high-frequency component from the low-frequency component. The high frequency is the carrier, while the low-frequency component is the message which we wish to receive. The carrier signal, having served its purpose, is discarded by the detector, but the detector passes the low-frequency signal, which is the message, on to a reproducer. The reproducer may be either earphones or a loudspeaker, either of which will convert the audio signal into sound waves to be heard by the operator. The drawing built up here is a block diagram of a basic radio receiver. All receivers share these features. These requirements may be met by the old-fashioned crystal set. The antenna is led through a coil to ground. The coil is inductively coupled to a tank circuit, which is tuned to the carrier frequency. This is fed to a crystal diode. A crystal diode is a semiconductor diode which passes current in only one direction and acts as a rectifier or detector. Across the circuit at this point is a small capacitor which provides a low impedance path for the carrier signal, but is high impedance to the audio signal. Since the audio signal cannot pass through the capacitor, it goes through the earphones, which reproduce the original message as it was spoken into the microphone at the transmitter. From this simple beginning, all modern radio receivers were evolved. This set of demonstration panels make up a working model of a modern super-heterodyne radio receiver. Notice that we still have our antenna, our tuner, our detector, and our reproducer. All the other parts are added to increase receiving efficiency. These additional circuits include a radio frequency amplifier, a converter, an intermediate frequency amplifier, a circuit for automatic volume control, a three-stage audio amplifier, and, of course, a power supply to supply energy to all the stages. Let's use a block diagram to see how all these circuits work together. Here we have our antenna, which is picking up signals of many different frequencies. Here is the tuner, which selects the frequency we wish to receive. Here is an RF amplifier, which makes the received signal stronger. Since these two are always connected together, we can combine them in one block. The strong radio frequency signal is fed to a converter where the frequency is changed. The converter includes a local oscillator. The high-frequency output of this oscillator is made to mix or heterodyne with the incoming signal to produce a difference frequency. This difference frequency is known as the intermediate frequency and is fed to the IF amplifier. No matter what the frequency of the received signal, the IF frequency is always the same. Since the IF amplifier handles only signals of this frequency, it can be made very efficient and with extremely high gain. Although the carrier frequency has been changed, the carrier envelope has not, and it still contains its original message. The strong IF signal goes into the detector, where it is split into its two original parts. The audio signal goes to this output. The carrier is converted to negative direct current, filtered, and sent back to the three preceding stages where it automatically controls the gain, making the receiver more sensitive on weak signals and less sensitive on strong signals. The audio signal goes to the audio frequency amplifier, where it is made strong enough to operate the loudspeaker. Now our receiver is complete, except for the power supply, which provides the proper voltages and currents for the various vacuum tubes. Now let's follow it through on the demonstration panels using the oscilloscope to observe some of the waveforms. Rather than pick up a station with our antenna, we shall inject the signal with this radio frequency signal generator. The RF signal generator is preferable for testing purposes because its frequency and amplitude can be controlled by the technician. Let's set the generator for a carrier frequency of 1 megacycle, and then operate this control to modulate the carrier with a 400-cycle test tone. These other controls permit adjustment of carrier amplitude and percentage of modulation. Now we connect the generator to the antenna terminals of the receiver and the oscilloscope to the control grid of the RF amplifier. Adjusting the tuning capacitor to resonance at the carrier frequency gives us maximum signal amplitude at the grid of the tube. With the double beam oscilloscope, we can see the output signal from this stage at the same time. The amplified signal is so much stronger that we must reduce the gain of the oscilloscope to make it fit the screen. The signal has been amplified approximately 5 times. Notice that the plate load in the RF amplifier is the coil L1. This is a radio frequency choke and presents a high impedance to any radio frequency. It is untuned. The signal developed across L1 is shunt-fed through coupling capacitors to the primary of T1. The secondary may be tuned to carrier frequency resonance with this tuning capacitor. This particular type of tube is known as a pentagrid converter. Pentagrid because it has 5 grids, and converter because it was specifically designed to function as a converter or mixer. Some of the grids function as part of the oscillator circuit, which is known as the local oscillator. This is a Hartley oscillator. The feedback is through this capacitor and the lower part of the tank coil. In this circuit, the cathode and the first grid are connected in the normal manner, but grids number 2 and 4 are connected together and act as a plate for the oscillator circuit. These 2 grids are wound with heavy wire and have close spacing, so that a large proportion of the electrons strike the conductors. Positive voltage is connected to these grids just as if they were a normal plate. Those electrons which miss these grid wires are attracted by the positive voltage on the actual plate of the tube. When the oscillator is working, the entire electron stream from cathode to plate is modulated, becoming stronger and weaker at the oscillator frequency. Also in the electron stream is grid number 3. This is the grid which injects our amplified carrier frequency. This signal also modulates the electron stream from here to here, so that the electrons are now controlled by 2 separate frequencies. You may well imagine that the two signals are thoroughly mixed together. This converter tube is acting as a nonlinear device. A device is said to be nonlinear when the output signal is a distorted form of the input. The oscillator circuit develops a very high negative bias across R2. This bias is large enough to ensure that the tube operates on the nonlinear portion of its curve. When two frequencies are fed into any nonlinear device, the output signal will consist of 4 different frequencies. An example may help to make this clear. We have already said that our carrier frequency is 1 megacycle, or to put it another way, 1,000 kilocycles. This is applied to grid number 3. The oscillator is tuned to 1460 kilocycles, and this appears on grids 2 and 4. Now, the output signal on the plate of the converter will consist of 4 frequencies. The difference between the two, which is 460 kilocycles, the sum of the two, which is 2460 kilocycles, and the two original signals, 1460 and 1000 kilocycles. Each of these frequencies contains the message modulation, which was present on our carrier signal. 3 of these signals are not required in the next stage. One of them is. The 1000 kilocycle signal goes to ground through this capacitor. The 1460 goes to ground the same way. The 2460 is lost in the same manner. But the 460 kilocycles is our intermediate, or IF frequency, and it is the one we wish to use. T3 is called an IF transformer, and both the primary and the secondary are resonant at 460 kilocycles. The primary is a parallel resonant circuit. This means that we have maximum impedance across the tank, line current is at a minimum, and circulating currents between the components are at a maximum. Since the impedance is high, the signal develops a large output voltage across the circuit. A large circulating current is set up through the coil, which gives us a very efficient transfer of energy to the secondary. Our signal has now reached the IF amplifier. This is a high-gain voltage amplifier. It is designed to work at maximum efficiency at the IF frequency. A pentode is used because it has a much higher amplification factor than the simpler triode. A pentode has 5 active elements: the cathode, plate, and 3 grids. Grid number 1 is the control grid and is similar to the grid in a triode. Grid number 2 is called a screen grid and must be connected to high positive voltage. Current flows in the screen grid, and any signal which develops on it is shunted to ground with this bypass capacitor. Grid number 3 is called a suppressor grid and is connected to the cathode. The screen grid and suppressor change the shape of the characteristic curve and provide a much higher amplification factor. The type of pentode used here is known as a remote cutoff pentode. The control grid has been wound with closely spaced turns at the ends and widely spaced turns in the center. If we plot a curve of plate current against grid voltage with the plate voltage held constant, it would look like this. Cutoff bias for this tube is about negative 40 volts. If the control grid were wound in the usual manner, with evenly spaced turns, the tube would be known as a sharp cutoff pentode, and the cutoff voltage would be approximately 7 or 8 volts. The reason we use the remote cutoff type in this circuit is that the gain of the stage may be varied over a wide range simply by varying the bias. If we have a bias of negative 20 and we superimpose a small grid signal, we get a small change in plate current. If we change the bias to negative 3 with the same input signal, we get a much larger change in plate current. Since the output signal is proportional to this changing plate current, you can see that the gain of the tube is high when the bias is low, and the gain is low when the bias is high. The plate load in our IF amplifier is another IF transformer, similar to the one at the output of the converter. Again, the primary and secondary are each tuned to the IF frequency 460 kilocycles. These transformers are adjusted to resonance with a non-metallic tuning tool as part of the lineup procedure. Our demonstration receiver has one IF stage, but most communications receivers have 3 or more identical stages for added sensitivity. When the IF signal has been amplified sufficiently, it is fed to a diode detector. A diode vacuum tube has only 2 active elements, a plate and a cathode. In this example, we have 2 diodes in the same envelope, but the 2 units are connected in parallel and act as a single tube. Remember that electrons flow from cathode to plate when the plate is positive. If the plate voltage is reversed, the current must stop. The electrons cannot flow in the reverse direction. We apply our IF signal from here to here. This signal is made up of 2 parts, the carrier signal at 460 kc and the audio signal. It is the function of the detector to separate these 2 parts. Let's have a good look at this signal on the oscilloscope. I'm adding this straight line to indicate 0 volts. Everything above it is positive, and everything below is negative. The audio frequency is contained in the fluctuating amplitude of the IF signal. If we wished, we could recover 2 audio signals. One is a fluctuating positive voltage, the other a fluctuating negative voltage. These signals are both the same and contain the same information, but they are 180 degrees out of phase with one another. In this circuit, we will recover the negative signal. You'll see why in a moment. Our detector will remove all the positive voltage above this line to prevent its interfering with our recovery of the signal. Let's remove some parts so that we can see their effect as we add them back into the circuit. First, the tube, then C1, C3, and C2. Now we'll connect the oscilloscope across R3. And move the second trace down so that we can observe the signal. R3 is variable and is used as a volume control in most receivers. Our output signal will appear across R3. Only part of the signal appears here because R1 is in series with R3, and the voltage splits between them. The full signal appears at this point. Watch what happens as the tube is plugged in and as it warms up. The positive peaks have been greatly reduced because the tube can conduct current in only one direction. Electrons leaving the cathode follow this path through the input transformer and return to the cathode through R3, always going from top to bottom or from negative to positive. Since this end of R3 is grounded, The other end must be negative with respect to ground. Now let's stretch our picture sideways and get a really good look at what's there. We see a lot of little negative pulses at the IF frequency. The audio signal isn't really there at all. To rebuild our audio signal, what we must do is join all these little peaks together. We'll put the picture back to normal now, so you can watch what happens as I reconnect C1. This has removed some of our radio frequency. Moving the oscilloscope, we can see the effect of R1, which reduces the RF still further. Enlarging the picture, we can see what is left. Now I replace C3, and our audio signal is complete. The capacitors have joined the peaks together. These two capacitors, along with R1, form a radio frequency filter. The time constant is carefully chosen so as to be long at the IF frequency and short at the audio frequency. Now we have our audio signal. The double beam lets us compare it with the carrier. But we still haven't finished with our detector. We'll move the oscilloscope to this terminal marked AVC. As you see, our audio signal appears here too. Remember, at this point, the audio signal is not alternating current, but rather a fluctuating negative DC voltage. Watch what happens as we put C2 back into the circuit. That gets rid of the fluctuations, and we're left with negative DC, which we can measure with this voltmeter. This is our AVC, or automatic volume control voltage. It is proportional to the strength of the carrier. If the carrier is made stronger, the AVC voltage becomes more negative. If the carrier is made weaker, it becomes less negative. We connect this voltage back to the IF amplifier, back to the converter, and back to the RF voltage amplifier, so that it will control the gain of all three stages. The other output from our detector was the audio signal. This is fed through a coupling capacitor which removes the negative DC component and is fed to the grid of an audio voltage amplifier. This makes it stronger. And feeds it into a phase splitter, which splits it into two signals which are equal in amplitude but opposite in phase. These are coupled to an audio power amplifier, where each signal is amplified in a separate tube and fed to T1. This is an audio output transformer, which recombines the out-of-phase signals and lowers their impedance to match the loudspeaker. The loudspeaker vibrates at audio frequencies and recreates the sound waves which are heard by the operator. This, then, is the super heterodyne receiver. The vast majority of radio receivers use the super heterodyne principle. There are many variations of these basic circuits, but the principles remain the same. In some equipment, the vacuum tube does not appear. In its place is the tiny transistor, which allows greater miniaturization of most of the parts of a radio receiver with equal or greater efficiency. A transistor is a small semiconductor device which performs most of the functions of the various vacuum tubes. Here is a transistorized converter. This is the transistor, and this is the schematic symbol. Here is our oscillator circuit, which compares with the one in the vacuum tube converter. Here are the IF transformers, and our tuning capacitor, which is much smaller than that in the vacuum tube circuit. In spite of the changes, the similarities are greater than the differences.